Hello everyone, I'm Luca Moschella and today we will talk about relative representation. This is a work we did in our lab, Gladia, in Sapienza, in collaboration with Francesco Logatello. In this work we deal with neural networks. Let's see what they are and how we define them. For us, they are composed by two components, an encoder and a decoder. So in abstract, we have some data that is given to the encoder. This data, that can be in any form, for example an image or a text, is embedded into a latent space, just a vector of numbers. And then this embedding is given to a decoder that solves a downstream task. We are talking about a general downstream task with a general decoder. So the decoder can have any dimensionality, and the downstream task can be anything. For example, one task could be generation, so generate some sort of data, classification, to classify some data into some classes, or reconstruct the same data, so a compression task basically. We will start with this talk by analyzing the shape of the latent space. And we will do so with a bidimensional autoencoder. So we are in the reconstruction task. In this example, we have some image coming to the encoder. This is embedded into a bidimensional embedding. And then these two numbers are given to the decoder that is able to reconstruct the same image. This is the whole process. And with this structure, we are basically able to visualize the bidimensional embedding in a 2D plane without any dimensionality reduction or visual artifact. So basically, we have that each point in a 2D plane is associated with a single image, and we can study how these images are displaced in the 2D plane without any visual artifacts. So, for example, this is the complete latent space for a trained autoencoder. And our first question is, which are the contributing factors to these shapes, to this shape? Why this autoencoder produced this latent space? Ideally, the data distribution, the task you are solving, and some additional constraint should be the only factor that influence the shape of the latent space. And here, for additional constraint, I mean architectural. For example, if you have some sort of activation, for example, a ReLU, a rectified linear unit that goes into the latent space, you can only have positive numbers in the latent space. So of course, you won't have negative points or some constraint in the loss, for example, some smoothness constraint. In practice, though, there are many factors that influence the latent space shape. For example, the parameter initialization, the data shuffling, the train seed, or other hyperparameters. And the goal of this work is to be invariant to these factors. So let's see an example in practice. Here on the left, we are training a bidimensional autoencoder on NIST. This is a data composed of handwritten digits. And on the right, we are training again the same autoencoder on the same data with the same task, but with a different random seed. So for example, we have different shuffling of the data, a different initialization for the parameters. And this is what we observe basically. This is the latent space as they evolve over time, as the two models are trained. Here we are visualizing the same data point, the same images, and the colors are the classes. So 10 colors, one for each digit, from 0 to 9. And as you can see, we obtain different latent spaces, even though the model, the task, and the data was the same. And I'm sure you noticed that these two are actually quite similar. So let's see, like one transformation to make them very similar. So let's start by considering two data points, two images, and their embeddings in the two latent spaces. For example, here we have two stars. So they are the same data points that are embedded by the two autoencoders in the two different stars. And then we consider each other sample. For example, this orange dot. And here what we do is compute a latent distance. So we are computing a distance not in the image space, not between the data samples, but in the embeddings. And we can use any distance we want. For example, Euclidean distance in this example. What we do then is performing a reference frame change so that we represent the orange dot and in general any point with the distances with respect to the stars. And in this new frame, the two spaces are very similar. So we basically were invariant to the factors we saw before. So what we saw is that sources of variations in the training process of different neural networks produce distinct latent spaces. Now our first question is, can we model how these distinct latent spaces are related? What is changing between them? And our answer is yes. And we can assume that there is an angle preserving transformation T that relates the latent spaces. So they can, for example, rotate, reflect, or each point can be independently rescaled. This is the sort of transformation that might happen between two latent spaces. Basically, we only care about the angle, not the norm of the points. So for us, they are like displayed on a hypersphere. So we need a representation that is invariant to T. And this is like the core idea of this work. Basically, we saw that there is something going on between the latent spaces. We observed that there is some transformation that models the variations, and we are searching for a representation that is invariant to that transformation. And these are what we call the relative representations. So let's see the algorithm to compute them. That is very simple, and you already saw them in action because it's basically all there is for their computation. So we start by selecting a subset A of the training set X, denoted by anchors. So in this example, we are selecting some images. Then for each other sample X, again images, another image, for example, we consider an encoding function E. Now the images are embedded into the latent space, so they become vectors. And we choose some similarity function to compute a latent distance between each anchor and the sample. Then these similarities, these distances, are our new representation for the sample. And this is what we call the relative representation of our sample X. There are some interesting properties for sure. And one important choice is which similarity function to use. And in our work, we use the cosine similarity. That, by the way, is very simple to compute, just like 3 lines of PyTorch. And moreover, it is differentiable. The properties are very interesting. The first one is that, as you notice, this is like an independent transformation for each space. So we can have the same transformation applied independently to each space without computing or estimating a transformation between two given spaces. So this is acting like an universal representation that brings all the spaces into a common one without knowing of each other. Moreover, we have that the size of the relative representation depends on the number of anchors, A, and not on the embedding dimensionality. So in theory, we could bring in the same space, latent spaces that had different dimensionality. Moreover, as I said, the choice of anchors and similarity function determines the representation properties. In this case, we have chosen the cosine similarity, and thus we are invariant to angle preserving transformations of the latent space. So this is like the core idea, and this is super simple. And if you have any question about that, feel free to post it on the chat or on Slack. I will be happy to answer. And then we will start seeing, we will see some application of this simple idea. We will start with this semantic invariance. Let's see what this is about. So say that we are given some words, English words, and we consider their embeddings in different spaces. So this is what they call word embeddings, and they are a way to represent the meaning of a word. there are different word embeddings types that are obtained in different ways. And these are two possible ways to obtain them, basically. The fast text word embeddings and the word2vec. They are ways to represent words. And here visualized, you are seeing the same words in both spaces, and the color at different semantic areas. So basically, we have 4 different words that represent very different concepts. For example, student, car, and so on. And we took similar words to these 4 words, and we obtained 4 different semantic areas, and just visualized them. These are the absolute spaces, so we didn't do anything basically. We just selected some sample and visualized them. Now we perform this relative transformation, and this is what happens basically. The 2 spaces that were quite different become very similar. This means that they were intrinsically similar. Our conclusion here is that latent spaces with the same semantics are represented similarly in the relative space. And for us, that was very surprising. The second application is the latent performance metric. Here we are in a completely different setting. We are on graphs, and we are considering a node classification task. So we consider some graph. For example, we use the Cora dataset. This is a graph composed of papers and citations between papers, basically. But the important thing is that each node here has a color. And the task is to assign the correct color to each node. And we assume that we are given a good reference model. And for us, a good reference model is a model that can assign the correct color to each node with very high accuracy. And then we do the following, basically. We train other models. And we want to plot them in this plot. So we have the reference model here on the upright part. On the y-axis, there is the performance. So the reference model is very good because it's in very up on the plot. And on the x-axis, there is the relative latent similarity to the reference model. Of course, the reference model is very similar to itself, so the similarity is 1. So this is on the upper right part of the plot. On the right, you can see the hyperparameters we used to train that model. So there are some, for example, the seed, the epochs, the optimizer, even some architectural, like the type of graph encoder, the graph convolution, or the optimizer, and so on. And then we do the following. We change some parameters on the right, and we obtain another model. This model here is represented by the blue dot. We'll have some other performance, of course, because we changed the parameter, and some other relative latent similarity to the reference model. It will be different, basically. And we continue doing so. So basically, we change parameters, we obtain other models, and we plot them in this scatter plot. And what we observe is very interesting because basically there is a correlation between the latent similarity to the reference model and the performance, a very strong correlation. Moreover, basically this relative space, basically this means that a relative space that is similar to the reference model means having good performance. So if you train a model that you know is similar to a reference model that you were given and you know that was good, that means that that model will be good, at least in our setting. Note that there is nothing to support the other direction. So you may have good performance even with a model that is not similar to the reference model, because there might be other latent spaces that are completely different, but still good enough to solve the task, or even better, we don't know. This is very interesting because this correlation also holds over time. So this is a single model that is training over, and you can see that over the epochs, the performance and the similarity still have that correlation. So as the performance increases, the similarity with the reference model increases. And that was very consistent in our setting. These were other models that we trained, and they all exhibit that behavior. The last application that I want to show to you is the zero-shot stitching. In this application, assume that you have two autoencoders trained, so they were like trained correctly, and they were converged, and they were able to they are able to reconstruct correctly the input digit. But in the absolute sense, and moreover, you have two autoencoders in the relative space, and that means that the decoder is trained on relative representations. You can do that because the relative transformation is differentiable. It's just a cosine similarity between the anchors. And then you do the following. You provide an image to the first encoder, and then feed the embedding to the second decoder. So basically, you are stitching together two independent parts of two different models. And that is not clear what should happen. In general, you would assume that's just broken, right? Instead, this is what happens. So on the first row here, you have the identity, so the source image. On the second row, you have a normal autoencoder. And as you can see, that's broken indeed. It just produces almost noise. On the third row, you have VA, a variational autoencoder. I'm not sure if you are familiar with those, but they are basically autoencoders, as you saw until now. But there is a constraint in the space to look like a Gaussian, basically. So there is a regularization on the latent space. This means that each point in the latent space makes sense, so it reconstructs realistic digits. The problem is that they are just wrong. If you see closely, you are reconstructing, for example, 4 with an 8. This is, of course, completely wrong. If you use instead a relative autoencoder and stitch together, always independently, always a zero shot, without ever fine-tuning or retraining or anything, but they were trained on relative representation, in this case, that works. In the paper, we also have this zero-shot stitching on classification over the CIFAR100 dataset and the ImageNet dataset. It worked surprisingly well. And moreover, here you can see that there are a lot of dashes in the absolute column. That is because if you don't use the relative representations, some models have different absolute embeddings sizes. So basically, their embeddings the encoder and decoder cannot be stitched together because they have different dimensionality. So you would need to train some stitching layer or do something. You cannot just take the two components and attach them together. So that is not possible. So that is why you have the dashes there. Note that this model were all pre-trained transformers, mostly, downloaded from Hugging Face, and we didn't fine-tune them, we just used them. And note that there is also a RexNet, so the stitching also works between different type of architectures. But, for example, there we have a convolution and a transformer. So that is like very surprising. Moreover, we did another experiment, more complex. Basically, we tried to stitch across languages. So we trained a classifier on English data, and then we wanted to reuse the same classifier without fine-tuning it on other languages. Basically, we stitched the English classifier on the spaces obtained by different encoders on other languages. And this is what we obtained. So this experiment was performed on the Amazon dataset. The Amazon dataset is basically a dataset of reviews in different languages, and each review has a star rating. And the task is to predict the number of stars that each review has given. So we basically train on a classifier. This is able to quite with quite good performance, predict the number of stars of an English review, and then predict that the number of stars on, for example, French or Spanish or Japanese reviews without ever fine-tuning the classifier on that language. So the building block for this application, for the derived representation to work, are the parallel anchors. Basically, parallel anchors are a partial correspondence between domains. So here the stars are the two set of anchors for the two spaces. And this is the partial correspondence. So basically we have anchors in the two spaces that represent the same concept. And then for every other sample, each dimension is obtained comparing the sample with the anchor that represents the same meaning. So in this example, the first dimension of the relative representation of the white dot is obtained comparing it with the concept of cat, for example, and so on for all the others. So we have that the same dimension represents the same meaning. So we have comparable representation, even though they are in different latent spaces. So to conclude, we have shown that zero-shot communication between different latent spaces is possible, and it finds application in model stitching, in measuring the performance of neural models, and in generalizing unimodal to multimodal models, as you have seen in the cross-language setting. And we also have another work that shows that it's possible to communicate between images and text zero-shot. Further directions are exploring, for example, exploring different invariances or properties infused by different similarities or similarity functions or anchor choices. Remember that we have chosen the cosine similarity, thus we are invariant to angle preserved transformation. There may be other similarity functions that produce other invariances that may be helpful in other settings. And moreover, the relative space similarity could be used as a supervision signal to train other models in a teacher-student setting. That is also a very interesting application where we basically provide directly a supervision signal in the latent space. So that is all. Again, if you have any questions, feel free to ask them on the chat or on Slack, and I will be happy to reply. Thank you so much for your attention.